Koranyi norm provides a very fast and efficient way to defining a distance on Heisenberg groups that ends up being bi-Lipschitz equivalent to the Carnot-Caratheodory distance at the end. Therefore, theoretically, it's much efficient than going through the business of horizontal curves proving that at least one curve exists between any 2 points and infimizing their length. We're going to introduce this norm and metric in this lecture. So far, recall that we have introduced the sub-Riemannian structure on Heisenberg group. It is a manifold being R2n plus 1. It's a non-abelian group, and that the default metric on it is the DCC distance defined through shortest horizontal curves. In the last lecture, we connected this notion of distance, which we had built before introducing the group structure on Heisenberg group, to be a left invariant one. That is, it respects the group structure. Notice that here I am using the complex notation where z stands for my point xy in the plane. And here z prime bar means the complex conjugate of z bar. This is just a different way of writing the multiplication formula, but it's very convenient as we don't have to decompose z and z prime into two components. When trying to prove connectivity of Heisenberg group by horizontal curves, we ended up proving the following estimate. There is a constant independent of z and t, such that the distance of zt to the origin is up to this constant comparable to absolute value z plus absolute value of t to the power 1/2. This was done manually by first projecting the point onto the xy plane and then joining it by a straight line to the origin, which is a horizontal curve. And then the square root estimate came from the isoperimetric inequality in joining, in path lifting circles to join 2 points that are vertically different from one another. So we want to start with this estimate and end up finding a norm, and then from that norm a distance that ends up being equivalent to DCC. A simple observation from calculus is that up to, I think, the constant square root of 2, and if that doesn't work, up to the constant 2. If you give me two real numbers, non-negative, it's comparable to squaring them and then taking the root. So raise both sides to power 2 maybe, and that's easier way of seeing it. I think, again, if you multiply one side by 2, the smaller side, then it becomes greater than or equal to the other one. So if I apply this twice to the above, apply twice, to see that the Carnot distance of zt to the origin, which is the, by the way, identity element of the group, is comparable to z to the power 4 plus t to the power 2 and then root 1/4. So you apply this star once to go 2 up in the powers, and then once you do it again you go another 2. So z goes to 4, t to the 1/2 becomes t to 1, and then t to 2. Okay, what is special about this side, unlike the simpler versions, is that it goes well with the group structure. So let's call this the Koranyi norm of the point zt. So any point in the Heisenberg group can be written as zt, and then this is defined to be the Koranyi norm. So basically this lemma is saying that it deserves the name. If you multiply two elements, their Koranyi norm is less than or equal to addition of individual Koranyi norms. So in the case of Rn, this is just plus the group operation, and this is the familiar norm inequality. So here we don't multiply, remember, still we add. It's the group operation that is different, not this part. So this I'm not going to prove. Again, it's a straightforward but technical lemma. Now, there are other observations that we can make about this norm. The Koranyi norm of a point is never negative, and it's zero if and only if the point itself is zero. Another one is that the Koranyi norm of any point equals the Koranyi norm of its inverse. Okay, and just these three observations here will be enough for us to define a metric, a new metric on the Heisenberg group. We define the Koranyi distance between P and Q to be the Koranyi norm of P inverse multiplies into Q. Let's write it even in more clean notation. H1 with this dk is a metric space. First of all, dk of P from Q equals 0 implies that, well, definition says this is P inverse Q K norm is 0, but for the K norm we had this property that only 0 has this property, and multiplying by P from both sides would mean that P equals Q. So that checks the first part of being a metric. dk of P and Q is norm of P inverse Q. But for the Koranyi norm, we have that this is equal to the inverse of this thing. And inverse of this element, even though the group is non-abelian, is always Q inverse times pk. But that, by definition, is dk of Q from P. Because per definition is not symmetric per se, because you take inverse of the first element and then multiply. That's why this one is dk of Q from P, and this one is P from Q. But fortunately, they coincide. And now the third part, which is the most difficult part, is taken care of by the difficult lemma about the Koranyi norm being actually a norm. So if you have PQ, so this takes care of the second and third part, which is the triangle inequality. We want to prove it. This is by definition P inverse Q, K norm. And now I can put P inverse. For free, I can put a third point. So R inverse Q. That's just group property. And now I break this into two pieces. And now I use this norm property that this is less than or equal to norm of each part. So plus the norm of R inverse Q K. And now by definition, this is equal to distance of P from R, and the next one is distance of R from Q, K distance. And by completing the triangle inequality, we have proven that this is indeed a metric. dk and dcc are a bi-Lipschitz equivalent. And this is just not locally, globally so. basically the proof is that both of them are left invariant, and then when you compare the distance to 0, we had the initial lemma that they are comparable. These very carefully. So take any 2 points, P and Q. Now dk of P from Q, by definition, will be, in fact, actually dk of, well, let's write definition, P inverse Q Koranyi norm, and that is dk of P inverse Q from the origin. But notice that dk of zt to the 0 for any zt is equal to z to the 4 plus t to 1, t to 2 1 over 4, which is comparable to absolute value z plus t to 1/2, and that we had seen was comparable to Carnot-Caratheodory distance of zt to the origin. That means when one of the points is 0, the distance to 0 in either metric is bi-Lipschitz comparable. So dk of P and Q from first line will be with the same constant. So if this constant is c, it will be exactly same constant here, comparable to dcc of P inverse Q 0. But now from left invariance of Carnot-Caratheodory distance, and that is very important here, that's why we did this proof previously, is the same as dcc of, well, multiplied from left by p, so that would be q and p, which is just dcc of p and q. And we have proven that for any pair of points pq, the two metrics are comparable up to this bi-Lipschitz constant c. So we can even say what this constant c is if we have the explicit bound from the original lemma given this comparison. So this is the key here. The left invariance is the key. The rest is probably just definitions. So what is the significance of this equivalence? Right? So if we think about it philosophically, for all Lipschitz questions, Lipschitz analysis, say, purposes, dk and dcc are the same. So if you are studying a question that has to do with the Lipschitz geometry of Heisenberg group, you can use either of these metrics. But dk is much more straightforward and simpler to define. So in papers that deal with the Lipschitz geometry, people forego all the background required for definition of DCC, horizontal distribution, horizontal curves, Cho's theorem, why horizontal curves always exist between any given 2 points. They bypass all of that and immediately define the metric by this dk, and maybe mention that it is equivalent, bi-Lipschitz equivalent to the homogeneous distance, to the Carnot-Caratheodory distance. An example of such a paper is this beautiful one by Terence Harris, an almost everywhere lower bound for Hausdorff dimension under vertical projections in the Heisenberg group. 2020. It tries to study if you have a set of certain dimension range and you vertically project it, how much dimension can its shadow lose. I searched the word left translation and multiplication or left invariance, and there were only 1 or 2 instances. Everything here is done with the Koranyi metric, and that is enough for the purpose of this paper because it's study of dimension, which is invariant under bi-Lipschitz changes in metric. The definition of Koranyi norm, very explicit, and the Koranyi metric, but still bi-Lipschitz equivalent to the more intricate Carnot-Caratheodory distance.